The Fourier transform decomposes a function of time into the frequencies that make it up, similarly to how a musical chord can be expressed as the amplitude of its constituent notes. The Fourier transform of a function of time itself is a complex-valued function of frequency, whose absolute value represents the amount of that frequency present in the original function, and whose complex argument is the phase offset of the basic sinusoid in that frequency. The Fourier transform is called the frequency domain representation of the original signal. The term Fourier transform refers to both the frequency domain representation and the mathematical operation that associates the frequency domain representation to a function of time. The Fourier transform is not limited to functions of time, but in order to have a unified language, the domain of the original function is commonly referred to as the time domain. For many functions of practical interest, one can define an operation that reverses this. The inverse Fourier transformation, also called Fourier synthesis, of a frequency domain representation combines the contributions of all the different frequencies to recover the original function of time. Linear operations performed in one domain have corresponding operations in the other domain, which are sometimes easier to perform. The operation of differentiation in the time domain corresponds to multiplication by the frequency. So some differential equations are easier to analyze in the frequency domain. Also, convolution in the time domain corresponds to ordinary multiplication in the frequency domain. Concretely, this means that in any linear time invariant system, such as a filter applied to a signal, can be expressed relatively simply as an operation on frequencies. After performing the desired operations, transformation of the result can be made back to the time domain. Harmonic analysis is the systematic study of the relationship between the frequency and time domains, including the kinds of functions or operations that are simpler in one or the other, and has deep connections to almost all areas of modern mathematics. Functions that are localized in the time domain have Fourier transforms that are spread out across the frequency domain and vice versa, a phenomenon known as the uncertainty principle. The critical case for this principle is the Gaussian function, of substantial importance in probability theory and statistics as well as in the study of physical phenomena exhibiting normal distribution. The Fourier transform of a Gaussian function is another Gaussian function. Joseph Fourier introduced the transform in his study of heat transfer, where Gaussian functions appear as solutions of the heat equation. The Fourier transform can be formally defined as an improper Riemann integral, making it an integral transform. Although this definition is not suitable for many applications requiring a more sophisticated integration theory. For example, many relatively simple applications use the Dirac delta function, which can be treated formally as if it were a function, but the justification requires a mathematically more sophisticated viewpoint. The Fourier transform can also be generalized to functions of several variables on Euclidean space, sending a function of three-dimensional space to a function of three-dimensional momentum. The idea makes the spatial Fourier transform very natural in the study of waves, as well as in quantum mechanics, where it is important to be able to represent wave solutions as functions of either space or momentum and sometimes both. In general, functions to which Fourier methods are applicable are complex-valued, and possibly vector-valued. Still further generalization is possible to functions on groups, which besides the original Fourier transform on or n, notably includes the discrete time Fourier transform, the discrete Fourier transform and the Fourier series or circular Fourier transform. The latter is routinely employed to handle periodic functions. The fast Fourier transform is an algorithm for computing the DFD. Definition. There are several common conventions for defining the Fourier transform of an integrable function. This article will use the following definition. For any real number xi, when the independent variable x represents time, the transform variable xi represents frequency. under suitable conditions, is determined via the inverse transform. For any real number x, the statement that can be reconstructed from is known as the Fourier inversion theorem, and was first introduced in Fourier's analytical theory of heat. Although what would be considered a proof by modern standards was not given until much later. The functions and often are referred to as a Fourier integral pair or Fourier transform pair. For other common conventions and notations, including using the angular frequency omega instead of the frequency xi, see other conventions and other notations below. The Fourier transform in Euclidean space is treated separately, in which the variable x often represents position and xi momentum. History. In 1822, Joseph Fourier showed that some functions could be written as an infinite sum of harmonics. Introduction. One motivation for the Fourier transform comes from the study of Fourier series. In the study of Fourier series, complicated but periodic functions are written as the sum of simple waves mathematically represented by sines and cosines. The Fourier transform is an extension of the Fourier series that results when the period of the represented function is lengthened and allowed to approach infinity. Due to the properties of sine and cosine, it is possible to recover the amplitude of each wave in a Fourier series using an integral. In many cases it is desirable to use Eulers' formula, which states that e2 pi I theta equals cos plus I sin. To write Fourier series in terms of the basic waves e2 pi I theta, this has the advantage of simplifying many of the formulas involved, and provides a formulation for Fourier series that more closely resembles the definition followed in this article. Rewriting sines and cosines as complex exponentials makes it necessary for the Fourier coefficients to be complex valued. The usual interpretation of this complex number is that it gives both the amplitude of the wave present in the function and the phase of the wave. These complex exponentials sometimes contain negative frequencies. If theta is measured in seconds, then the waves e2 pi I theta and e minus 2 pi I theta both complete one cycle per second, but they represent different frequencies in the Fourier transform. Hence, frequency no longer measures the number of cycles per unit time, but is still closely related. There is a close connection between the definition of Fourier series and the Fourier transform for functions f that are zero outside an interval. For such a function, we can calculate its Fourier series on any interval that includes the points where f is not identically zero. The Fourier transform is also defined for such a function. As we increase the length of the interval on which we calculate the Fourier series, then the Fourier series coefficients begin to look like the Fourier transform, and the sum of the Fourier series of f begins to look like the inverse Fourier transform. To explain this more precisely, suppose that t is large enough so that the interval minus t2 contains the interval on which f is not identically zero. Then the nth series coefficient Cn is given by comparing this to the definition of the Fourier transform. It follows that since f is zero outside minus t2, thus the Fourier coefficients are just the values of the Fourier transform sampled on a grid of width 1 t multiplied by the grid width 1 t. Under appropriate conditions, the Fourier series of f will equal the function f. In other words, f can be written, where the last sum is simply the first sum rewritten using the definitions xi n equals n t, and delta xi equals t minus n t equals 1 t. This second sum is a Riemann sum, and so by letting t infinity it will converge to the integral for the inverse Fourier transform given in the definition section. Under suitable conditions this argument may be made precise. In the study of Fourier series, the numbers Cn could be thought of as the amount of the wave present in the Fourier series of f. Similarly, as seen above, the Fourier transform can be thought of as a function that measures how much of each individual frequency is present in our function f. and we can recombine these waves by using an integral to reproduce the original function. Example: the following figures provide a visual illustration of how the Fourier transform measures whether a frequency is present in a particular function. The function depicted f equals cos e minus pi t2 oscillates at 3 Hz and tends quickly to 0. This function was specially chosen to have a real Fourier transform that can easily be plotted. The first image contains its graph. In order to calculate, we must integrate e minus 2 pi if. The second image shows the plot of the real and imaginary parts of this function. The real part of the integrand is almost always positive because when f is negative, the real part of e minus 2 pi I is negative as well. Because they oscillate at the same rate, when f is positive, so is the real part of e minus 2 pi I. The result is that when you integrate the real part of the integrand, you get a relatively large number. On the other hand, when you try to measure a frequency that is not present, as in the case when we look at, you see that both real and imaginary component of this function vary rapidly between positive and negative values, as plotted in the third image. Therefore, in this case, the integrand oscillates fast enough so that the integral is very small and the value for the Fourier transform for that frequency is nearly 0. The general situation may be a bit more complicated than this, but this in spirit is how the Fourier transform measures how much of an individual frequency is present in a function f. Original function showing oscillation 3 Hz. Real and imaginary parts of integrand for Fourier transform at 3 Hz. Real and imaginary parts of integrand for Fourier transform at 5 Hz. Fourier transform with 3 and 5 Hz labeled.